Today we will be talking about the third and final reaction mechanism for year 12 chemistry, and that's radical substitution of alkanes. When an alkane meets a halogen molecule and they are exposed to light, they can form a haloalkane. This is because the UV light in the sun provides sufficient energy for such a reaction to happen. This could be the reaction between a chlorine molecule and methane. Now let's talk about how it actually happens. The mechanism takes place in 3 steps: initiation, propagation, and termination. In the initiation step, the UV light in the sun provides necessary energy to start the reaction by splitting the bond in the halogen molecule. I've already discussed fission in the past, but homolytic fission is when you break a covalent bond and each atom takes one electron from the electron pair. This can be drawn as so. The half arrows, sometimes called fish hooks, represent the movement of one electron from the bonding pair going to each atom from the original halogen molecule. Anyways, this homolytic fission results in the formation of 2 halogen atoms with an electron each from the bond fission. We call these atoms radicals. A radical is any reactive species with an unpaired electron. These radicals will then carry on to the second step, propagation. So these radicals proceed to react with the alkene molecule, and in effect, they steal one of the hydrogens off the alkane. This caused the formation of a hydrogen halide, but also an alkane radical. And the reason why the alkane became a radical is because now it has an unpaired electron on the carbon. This alkane radical then goes on to react with an unbroken halogen molecule to form a halogen radical and our desired product. Now you might notice that a radical goes in and a radical comes out. This regeneration is incredibly important because this means that in theory this reaction could go on forever. One sec. It could go on forever. In fact, it can go on for 1 million times before it stops. This happens when 2 radicals collide during the termination step. The termination step occurs when 2 radicals collide. Since we have 2 radical species in this reaction, there are 3 possible termination steps. First step is between 2 halogen radicals, which provides us with our original halogen molecule. Second termination step is with the 2 alkane radicals, which provides us with an entirely new hydrocarbon. And finally, we have a reaction between the halogen radical and the alkane radical, which provides us with our desired product. Now there is a handy way to identify what type of step a reaction is, and you just got to look at the radicals. If it is an initiation step, there will be no radicals on the left side and 2 radicals on the right side, so that's an initiation step. If it's a propagation step, there will be 1 radical on the left and then 1 radical on the right. So these 2 are propagation steps. Now, for a termination step, you have two radicals at the start and no radicals at the end. So all these three are termination steps. Finally, let's talk about the limitations of this mechanism. Imagine a pros and cons list. The pro is that it forms haloalkanes. The cons are a bit more extensive. The first one is that radical substitution can lead to further substitution. What I mean by this is that there's nothing stopping our product from getting resubstituted until eventually all the hydrogen atoms have been swapped out for halogen ones. The second con is that whilst for methane we can sort of select what carbon the hydrogen is substituted from, because there's only one carbon. For a molecule like propane, there's 3 carbons, so the hydrogen that is substituted could be from either 3 of the carbons, and you can't control that. So that's why you don't use radical substitution for single product synthesis.